far what we've been dealing with are paired data. So either you can take your paired data and do the time test, which is look at the number of positive differences and see if that's abnormal. Or you can take your paired data, look at the differences, add up all of the positive ranks, and see if that's abnormal. But what about when we have two samples that are not paired? And when we have two samples that are not paired, we use what's called the Wilcoxon rank sum test. And so for the steps of this test, we're going to do it in, let me read out the question. We wish to compare length of stay in the hospital for patients with the same diagnosis at two different hospitals. So we're comparing length of stay at two different hospitals, and here are the lengths of stay in hours for the first hospital and the second hospital. You can see that the first hospital, we'll call it N sub S because that's the smaller number, and N sub L, they're different. So now we have different numbers in each sample. N sub S is 11, N sub L is 13. Okay. So what do you have to do? So this is for, remember this test is for unpaired data. So the first step is combine all the data into one group and put in ascending order. Okay? So let me do that. So I'll put the hospital and the actual hours. You can see that hospital 1 has one value of 5. The first hospital has a value of 5, and then 8. And that's also with the first hospital. And then 10, but there are two 10s, one at the first hospital and one at the second hospital. Okay. So I'm just taking these data points and putting them in increasing order. Okay. So there's 13, 21, these are all at the first hospital. 26, that's also at the first hospital. 27 and 29, that's at the second hospital and that's at the first hospital. 32, 33, these are also both at the first hospital. 35, that's at the second hospital. There are two 44s, one at the first hospital, one at the second hospital. They're also 6, one at the first hospital, one at the second. And there are more data points, but the rest of the data points are only in the second hospital. So you can just stop right there. Once you've accounted for all of the points in the smaller group, you can stop. And you can rank them. So ranking them is just putting them in order. So this is rank 1, 2. This would be 3 and 4, but you take the average of that, 3.5. This would be 5, 6, 7, 8, 9, 10, 11, 12. This would be 13 and 14, so you take the average of that to be 13.5. This would be 15 and 16, so you take the average of that to be 15.5. Okay. So, first step, combine all the data and put it in ascending order. Second step, rank them. And you should evaluate the tie. The third step is add the ranks of the smaller group. You call that W. And this W is, again, is also normally distributed. And what is the expected value of W? It's very similar to the time test. If you the number in the small group divided by 2, theory as the first step that we did, the sign step. The standard deviation on this number is the square root of n sub L s times n sub L times n sub s plus n sub L plus 1 all over 12. And we can plug that in. That's just the square. In this case, it's the square root of 11 times 13 times 11 plus 13 plus 1 all over 12. And when you calculate that out, it just becomes 17.8. When you calculate what the new value is, that's equal to 11 over 2 times 25, and that's equal to 137.5. The values don't mean anything, it's just the process that we care about. And like I said, remember where these come from. The standard deviation just comes from that basic idea that standard deviation of a binomial distribution is square root of n cubed. So I'm throwing a lot of equations at you. I'm not really deriving them. You could derive them, and it would take forever. It all goes back to what I showed on the board with the standard deviation is equal to square root of n cubed. That's where this comes from. Yeah, that 12 will always be 12. This equation is just too general. Right. So then the last step is to actually carry out the calculation of mean. We carry out your calculation. Mean is just equal to W minus the expectation value of W, mu is the mean of W, all over the standard deviation. In this case, that's equal to, you put out two values on W. In this case, that's equal to 83.5 minus 137.5 over 17.3. And I forgot a step in there. I didn't show you what W was. When we're adding all the ranks of the smaller group, we're just adding up all the ones from hospital 1. So 1 plus 2 plus 3.5 plus 5 plus 6 plus 7 plus 9 plus 10 plus 11 plus 13.5 plus 15.5. When you add all those up, you get 83.5. So we take that sum and we say, how different is that from what we would expect it to be? And what we expect it to be is 137.5. We calculate the z-score. That's equal to 3.12. Okay? So much greater than 1.96. So we can reject the null hypothesis. Say that the two groups are different. So
What is the method for taking into account the actual values the order?
yes, it's only taking into account the order because you can't take into account the actual value when you're the magnitude when you're, why would that help you here? Assuming you can't assume that the underlying distribution is normal. So that's why in all of these tests, the non-parametric tests, we're interested in not the means of the population, we're interested in comparing the medians of the population. That's why we rank them. And then we're taking we're looking at the magnitude of those ranks. Because that's what we're doing when we add up the sum of the positive ranks. We're looking at the magnitude of the ranks. We're not looking at the values of the actual data point. The way we take magnitude into account is by adding up the ranks.
But intuitively, it makes sense that you adjust the point of value going down
you add up all the values of the data points,
No, like in honor of if you were to change some of those values, what would it come that way?
it wouldn't make a difference.
It does make a difference. So it's good if you add
It doesn't make a difference because the underlying distributions are normal, there's always going to be that error that shouldn't make a difference.
You stop ranking them as soon as you have only one group left.
Yeah, as long you stop ranking them after you've gotten done with the smaller group.
Okay.
So once you finish with all the data points in the smaller group, which could be that you have to go all the way to the end
How small
of the group with the smaller number of names. I know I'm throwing a lot of equations out on you. Let's just quickly review what we've done. And remember, the most important thing for the purposes of statistics is just being able to manipulate these equations. And hopefully you guys understand where it's coming from a little bit. But I'll just review what we've done. So non-parametric methods, we're dealing with data that you cannot assume is normal. If you have paired data, you can do a test known as the sign test, where you take all the differences for n pairs, you count the number of positive differences, and you expect that the number of positive differences divided by the total number of differences should just be a half. So if this follows a normal distribution, where d is the number of positive differences, n over 2 is the number that you expect, and the standard deviation is just the square root of n over 4. You use this equation only if n is greater than 20. If you have paired data, you don't need to use the sign test. You can also use what's known as the sign rank test, because this takes into account not only the magnitude, not only the sign of the differences, but the magnitude of the differences. And all you need to do is you put the differences in decreasing order and rank them. You then take the sum of the positive rank, and then use this for that. And this is all in the review handout. If you're not dealing with paired data, you do what's known as the Wilcoxon rank sum test, which is also known as this Mann-Whitney test. It's for unpaired data. You combine the data into one group, put them in ascending order, you rank them, you add the ranks of the smaller group, and you compare them to what's expected using the group. That's it. If you guys can understand this part of what we did, let's see, on the last page, you'll definitely have it. The question is, you guys understand this stuff? Does this stuff make sense? Yes. Good. You guys need to do the problem set. But I guarantee you, if you understand everything from this point preceding, you will pass that. And we still have to cover binomial proportion and then survival. You guys should definitely learn survival, though, just to And what if you make a mistake on the exam? You don't want to be 2 points away. Any questions on this? We're going to next take a 5-minute break, and then we're going to go. All the rest of them are going to be on the board.
So the sign test, which is the sign rank test, they're both for paired data, and it's just that the second one is always more powerful.
Yes, the second. So when you compare the sign test and the sign rank test, the second one is more powerful. We should always use that one, unless they tell you to do the sign test. You use that. Okay, let's take a 5-minute break. No, everything you want. You can bring notes, book. You bring your book. You can bring everything. It's a completely open book. Hey. Yeah. $5:30. Yep.
I was going to ask you how you calculated S8, because I couldn't figure it out.
Which one? Oh, the standard in the paired t-test?
Yeah.
Well, you just take the differences. So you have the list of your
the values of your differences. You take the mean of that list, and then you take the standard deviation.
Yeah, I couldn't figure out the formula for the standard deviation because I didn't get the numbers right.
Oh, of course. I mean, you just have these numbers, right?
Yeah.
Standard deviation is just equal to, there's two ways to do it. It's the sum each xi value minus x average squared over n minus 1. Or it's also equal to the sum of xi squared. This is all over 1 minus
Yeah, but these are
n x average. What do you mean two groups? Oh, but it doesn't matter. You can have it into one group. Because if you got 10 and 5 and then 4 and 6. Now you convert it into different groups, 5, 6, and 4. So now you just look at the standard deviation.
So I'm actually, that x bar is actually my mean difference.
This x bar is the
I'll try it again, because that's what I thought I did, but I still didn't get the numbers.
Okay.
You know when you're doing like a pair t-test,
Yep.
you get a negative number, right? You get like a negative number for your t-value, right?
Oh, I mean, just take the positive of it.
So you just take the positive.
Yeah, because it's an absolute value on the
What
top.
was the thing that we did where you got a negative number and then instead of subtracting from 1, there's an example last week where...
That was power. That was power.
Okay.
Because if you, in that case,
Yeah.
because you're dealing with two distributions, you're overlapping. Your d is negative, that means take this area to be your beta. If your d is positive, then the cutoff line that you're dealing with comes in between the mean. So your power becomes this part of the area. So it just makes the difference 1 minus. It's either this area or 1 minus area.
Maybe it was just beta.
Well, it's always 1 minus beta. The power is always 1 minus beta. But which area is your beta? It's always to the left of the cutoff in this case, right?
Yeah.
So where is your cutoff? If your d is negative, it's outside the mean. So this is all beta. So your 1 minus beta is much smaller.
Okay.
Does that make sense?
Sure.
This is the standard deviation. Is it the square root of the variance? But milking the food for all it's worth is an interesting one. No. Milking the parental supply of food.
Okay, and are those for us to pick up or just...
Yeah, those are handouts from last time that are on the web now. But yeah, definitely, if you haven't picked it up, pick it up.
Hey, can I ask you a quick question?
Sure.
So in the first problem set, on question 5, you assumed that his blood pressure is, the standard deviation is that representative of a population.
Yeah, his population of blood pressures.
So, but since it's an individual person,
Doesn't matter. He still has a population of blood pressures.
Okay.
Like a million of them. You can take a million measurements from one person. So
Okay.
it's sigma.
So
In other words, you use the z-test.
Right. That's why I was wondering why it wasn't a t-test instead of the z-test.
Because it's not a sample. If you take the standard deviation of just these 4,
Then that would be a t-test.
then that would be a t-test.
But if they give you something like this, then you automatically assume that that's the population value.
No, I mean, they'll say the standard deviation of the population. Or the standard deviation here
Of his blood pressure.
of his blood pressure, which is the population. So that's tricky. Yes.
What's missing is something here. I mean, this answer doesn't make sense.
No, assume that the distribution of birth rates in the general population is normal. Which suggests that oh, it's missing something above there. Yeah. I'm gonna have to look this up. Assume that the distribution of birth rates in the general okay. I'll have to check it out.
Okay.
Let me see if I have that. Can you email me about that? And then I'll email the class. Thank you.
tomorrow.
Yeah. Okay, so next, so we're looking at October, so definitely. Yeah.
Hey, how's it going? Is it looking better or no?
It's really clear.
Great.
But I think I figured out a way that you don't have to turn on the lights. That I can still focus on the
Okay.
screen. I just make it darker on my screen. So if it's bothering you to turn on the lights, you don't have to.
Okay, but I'm going to go to the board anyways now.
Okay, good.
Is the board everything okay?
Yeah, it's always clear.
Okay, thanks a lot.
No problem.
We need another battery. Yetza, if you can hear me, we need another battery. Wow, you're quick. We need another battery. So let me just ask, are you guys able to, have you been doing the problem sets? Alright, so it's very important for you guys to do that, because remember, this test is not going to be easy. It's not going to be a joke, and if you can just do the problem sets, you'll be fine. I guarantee it. So, other than that, is everyone having a good weekend? What's so funny? No. You guys love Mech 209, right? You're in HST, get over it. That's what MIT is for.
I think that's okay.
Oh, that's perfect, thank you. Yeah, before the light wasn't going on. Thank you.
Okay, no problem.
Let's all give a round of applause for Yetza. She's doing an excellent job. All right. Can you guys hear me now? It's better? Okay. Okay. So we know how to deal with data that is normal, that where the underlying distributions are normal. There we use either the z-test or the t-test. We know how to deal with one sample versus two sample comparisons. One sample you can use the z-test or the t-test. Two samples you either use the paired t-test or the regular two-sample t-test. That's assuming everything is normal. Now we've dealt with non-parametrics where we cannot assume that everything is normal. And the last step, which is very easy actually, so just a logical extension, is comparing different proportions. That's our next step. Now again, when we're dealing with proportions, we're dealing with the binomial distribution. Okay? So, as we had already gone over, as long as NPQ is greater than or equal to 5, you can use the normal approximation, where z, the normal approximation, equals whatever you're looking at, x, minus np, the average, over the square root of npq. Okay? That's our z statistic, where we have mean of np and standard deviation of square root of npq. But the way we're writing this equation, it deals with the number of events. That's how we're looking at this equation. Yeah. And I always go back to the same example of flipping the coin. So if we're tossing a coin 10 times, so our example is flipping a coin 10 flips. That's our n. Okay. And so our average number of heads is equal to np, which is 10 times 1/2, or 5. So all of our numbers deal with events. 5 heads for a total of 10 flips. But there's another way of looking at this same example, and that's just leaving everything in terms of proportions. Okay? And if we left everything in terms of proportions, we would say, okay, the probability of a head, p, is 1/2. Okay? And so we could come up with a distribution where that probability of 1/2 is at the center. You know, that's our probability of a head. And so then we could ask the question, what's the likelihood of getting a probability of 0.9 for a head? Okay. So not only does the number of flips, number of heads follow this distribution, going from 0 to 5 to 10 heads, but you can also do it in terms of proportions, 0 to 1/2 to 1. Okay? Where we're looking at the proportion of heads instead of the absolute number. So this is not complicated. All it does is changes the following, and I'll put this quick table up to show you. So that when we're dealing with number of events, our mean, our standard deviation, and our z becomes np square root of npq, and this is x minus np over the square root of npq. When we're dealing with proportions, all we're dealing with is everything without the n. So we're dividing everything here by n. And what we get here is P is the probability that we're getting. If we divide the standard deviation by n, what we get is PQ over n. That's our standard deviation around the proportion, 1/2. Okay. And our z statistic now becomes P minus P naught over the square root of PQ over n. That's all we're doing. We're taking our binomial distribution and looking at it either in terms of the number of events or the proportion. P naught is just the probability in the general population. Like that would be our 1/2. Okay. So I would call this P naught. That's our 1/2. P, this is for our sample. And when we're dealing with samples, we either call it P or we give it the symbol P hat when we're dealing with the probability of a sample. Sorry, yeah. If you know it, it's P naught, Q naught. P naught is when the probability in the entire population. So if we had 1 million coin flips, we would know that half of them would be heads. So P naught is 1/2, that's of the general population. P is that of the sample, or you can also call it P hat. Okay. Our standard deviation is now a little different. It's no longer the square root of NPQ. You have to divide it by n, so it's now square root of P naught Q naught over n. Okay. And so a lot of times in statistics, we look at things based on proportions. And we can, we can make 95% confidence intervals around our proportions. So the 95% confidence intervals around our P naught, would be equal to, just like always, P naught plus or minus 1.96. But now what is our standard deviation? It's P naught 1 minus P naught over n, the square root of that. So that would be our 95% confidence intervals around that fraction of heads, which is 1/2 in this example. Okay? And we can do sample comparisons. So if we're doing one sample comparisons, and we know P naught is the probability in the population, and P hat is the probability in our sample, we can test the null hypothesis. Does P naught equal to P hat? And the alternative hypothesis would be, no, they don't. And the way to set it up is, you set up your z-test. Okay. It's P hat minus P naught all over the standard deviation. What's our standard deviation in this case? Which one do we use? Do we use P hat or P naught? P naught, because that's from the whole population. P naught 1 minus P naught over n. That's our z-test. Is there such a thing as a one-sample t-test here with the binomial distribution? Would there be such a thing as a one-sample t-test? When do we use a one-sample t-test? But we don't know the population standard deviation. Would we ever have that situation here? Right. Just by knowing P naught, the average probability in the population, as long as we're making the assumption that it's normal, we know that it's binomial, as long as we know that NPQ is greater than 5, so we can assume that it's normal. We know that the standard deviation of the population is just the square root of NP times Q. So we're never left in the situation where we don't know the standard deviation of the population. right? Because we do. As long as we know what the average is in the population, the average proportion, we can just calculate from that what the standard deviation is of the population. So all I'm trying to say is that there is no such thing. When we're dealing with proportions, there is no such thing as the one sample t-test. We're always using the z-test. All right, let's do some examples. That'll be the best way. So the first sheet on the handouts from today, let's get that out. And I think I'm going to stick up with the board for this. So those people following along in the video, go to the first page of the handout for today's lecture. And we're going to do the first problem on inference of proportions. Okay. So we're doing inference on proportions. And so we're studying the relationship. We're interested in studying the relationship between perinatal growth failure and cognitive ability. And what we get is that we do this study that of 33 infants with perinatal growth failure, 8 have IQs less than 70. Okay? And so we're defining P of our sample as the probability of having an IQ less than 70 for this population. And that's very simple. It's just 8 over 33, which when you plug in the number is 0.242. Okay? So that's what we're dealing with. So the first question is, what are the 95% confidence intervals around P? Well, what do we do? Yes, Salil.
We don't have P.
We don't have what? You're right, we don't have P naught. Do we need P naught? Well, that's okay. You can do the 95% confidence intervals around the population mean, or you can do the 95% confidence intervals around a sample mean. It's the same equation. You just use the P. You use the standard deviation of your sample now, of P hat, and you can assume that's normal. So we can still use the Z statistic as long as NPQ is greater than 5. So that's the thing. Whenever we're dealing with a binomial proportion, as long as NPQ is greater than 5, we can make the normal approximation. Right? And so we don't have to deal with t-tests. We're only dealing with z-tests. Okay? Okay, so is NPQ greater than 5? So it's 33 times 0.242 times 1 minus 0.242, right? And when you do that, you get that it's equal to 6.1, which is greater than 5. Okay? So, good, we're all set. This sample can be approximated as normal. We don't have to deal with any t-tests. All we're dealing with are z-tests. Okay, so the equation for the 95% confidence interval is P plus or minus Z of 0.975, because it's two-sided, times the standard deviation, P hat, 1 minus P hat, over N. In some ways, it's, for this very reason, it's easier to use the binomial, deal with binomial proportions rather than other distributions, just because you never have to worry about the t-test. So P is just 0.242 plus or minus Z of 0.975, which we all know is 1.96 times the square root of 0.242 times 1 minus 0.242 all over 33. Yes.
The earlier, when we addressed confidence intervals for
Right.
but then use the t when we see how.
Exactly. So prior, when we weren't dealing with proportions, we were dealing with just numbers. When we were calculating the 95% confidence interval around a sample, and we didn't know anything about the population, we would have used the t-test, the t-statistic. This would have been t of 0.975. All right. And when you just do out the math, it comes out to be 0.096 and 0.388. So what does this range tell us? Because we only have the probability of this sample, 0.242. What does this range tell us? We're 95% confident that the true probability of the population lies within this range. Okay? That's what we know with this 95% confidence interval. Okay, let's go to part B. If you were to select repeated sample sizes of 33 from this population of children with growth failure, what fraction has a sample proportion of 0.3 or more? So how do we do that? So n is 33. We're taking these repeated proportions, repeated sample sizes of n of 33. And we're going to assume, right, that our mean probability is the same as our sample probability of 0.242. And what's the standard deviation of this? What's the standard deviation of this population? Of this distribution? Well, that's just going to be the square root of p hat, 1 minus p hat over n. Right? So the square root of 0.242, 1 minus 0.242 over 33. And when you calculate that out, that's equal to 0.075. Right? So remember what we're doing. We're taking multiple groups of 33 people, finding their probability, and making a distribution. And that distribution will have a mean of 0.242 and a standard deviation of equal to that. And so now the question is how many of those groups will have a proportion greater than 0.3? So very simple. You just draw your line here and say this is 0.3, and we're looking for this area. This is just like dealing with a normal distribution. So you calculate your z-score. It's p minus p hat all over the standard deviation. P hat 1 minus p hat over n. Right? And then you just plug in the numbers. 0.3 minus 0.242 over the standard deviation of 0.075. And when you do that, you get that your value is 0.773. So this probability of 0.3 is this number of standard deviations away from the mean. So you now look back at your normal tables. Is this a one-sided or two-sided test? One-sided, we're only interested in those values greater than 0.3. So we calculate that area. When you look at your normal tables, you get that the area is 22%. Okay? Yeah, you assume that 0.242 is the mean of the population. Which is fine. You can do that. You guys okay? This is all we're doing is we are simply dealing with normal distributions, but now we're dealing with them in the context of proportions. Okay? All right. Let's do part C very quickly. So part C says that 3.2% of children with normal growth have an IQ less than 70. So P naught in the general population is 0.032. Okay? So the question is this also true for children who suffer from growth failure? So the question is asking, is this proportion of 0.242 of those infants suffering from growth failure, is it statistically the same as this of normal children, normal infants? So what we're doing is we're doing a one sample comparison, right? Where P is 0.242 and our Z, what's the equation for our Z? It's behind me. There you go. That's our equation for our Z. Which standard deviation are we going to use? Are we going to use the 0.075? We are now doing something different. We're comparing our one sample to the entire population of normal children. So which standard deviation do we want to use? We want to use the one of the entire normal the normal children population from 0.032. So we use P naught 1 minus P naught over n. Our n is still our 33 from our sample. That's our sample size. Okay. And so when you do that, it's 0.242 minus 0.032 over the square root of 0.032, 1 minus 0.032 over 33. And when you calculate that out, that gives you 6.85. That's your z-score. Much bigger than 1.96. So if it's much bigger than 1.96, you can say we reject the null hypothesis, and we say that P naught is not equal to P hat. That's our conclusion. The two proportions are different, statistically. Okay? So far, so good? All right. So this is sort of the same stuff we've been doing all along, except now just dealing with it in terms of proportions. That's all we're doing. Now, the next example is we'll talk about power. With power, it's a little bit trickier. We've already done power, where we've had two different distributions overlapping. And when we're dealing with proportions, there's another method that you use. So, same thing as before. We have two overlapping distributions. And before, their averages were mu naught and mu 1. But now we'll call it P1 and P naught. Okay? And again, you can draw your cutoff anywhere. Let's just say this is our cutoff. And we'll call that P. And everything above that, we'll say, okay, if we get a value that's above P, then we'll assume that the two distributions are different. Okay? So our null hypothesis is that P1 is equal to P naught, and our alternative hypothesis is that P1 is not equal to P naught. Okay? So we'll say this is our cutoff. Everything greater than this, we'll accept the alternative hypothesis. But there's some error in that. What is this error called right here? Alpha, also known as a type 1 error. And there's also this error right here, which is called what? Beta, type 2 error. Okay. And just to review, beta is the probability. Well, what are we going to do here? If it's in this part of the curve, we're going to accept the null hypothesis. given that the null hypothesis is false. That's what this probability is. So 1 minus beta is defined as the power of the study, and that's the probability of rejecting the null hypothesis given that the null hypothesis is false. And that's a measure of the strength of the study. It's our ability to detect a difference between the two groups. Well, before, when we were dealing with mu naught and mu 1, we just assumed that both populations had the same standard deviation sigma. Okay? But here, you don't have to do that. You didn't have to do it in the past situation either. Okay? You didn't have to assume they had the same standard deviations. Here, they're going to have their different standard deviations. This one will have a standard deviation P1, 1 minus P1 over n. And this one will have its standard deviation P naught, 1 minus P naught over n. Okay? So let's just say in this case we're going to say that they have different standard deviations, these two, and that we can't assume that they're equal. And let's derive the equation for power. So all you do is you use this value, P, and this cutoff in terms of the first distribution, right, in terms of the P naught distribution, is equal to P naught plus Z of alpha, and you use 1 minus alpha over 2 if it's a two-sided test, times the standard deviation of that population, P naught, 1 minus P naught over n. That same cutoff value can be described based on the P1 distribution as being equal to P1 plus Z of, now we're dealing with 1 minus beta, right? That area here is beta, so everything before it is 1 minus beta. So 1 minus beta times the standard deviation of that population, which is the square root of P1, 1 minus P1 over n. So what we're doing here is we're solving for the power, okay, when we have two distributions of unequal variance. Could we have assumed that both distributions had the same variance? Yeah, we could have. We're just doing it a different way right now. And so when you set these equal to each other, right? When you set these two equal to each other, you can solve for the power, which comes from this term, or you can solve for the sample size needed to obtain a particular power. So I'm not going to go through all the algebra. You can do it. How come? No, hold on one second. I made a mistake here. This is a minus sign, right? Because it's P1 minus Z. We're going backwards. So this should be a minus sign. Okay. But you can set the two equal to each other and solve for anything. So I'm going to skip this next problem, but you guys should do it. And when you do it, the answer is 341. I want you guys to do that on your own because we're running out of time. So, did you have a question?
Can you quickly explain again why P naught plus Z is 1 minus alpha over 2?
It's just notation. I mean, essentially you're just looking for the Z value for alpha point. No, again, alpha it's based on your null hypothesis. If your null hypothesis is that they're equal and that the alternative hypothesis is that are they different, if that's what you're asking, then it's a two-sided test. And that's, just like always, alpha can either be for one-sided or two-sided. It's this beta, once you've determined whether it's a one-sided or a two-sided test, you've restricted alpha, right? Then beta is the one that's always just one-sided. Okay? All right. 341. So just do that question. We're going to skip it for now. 341. 341. And let's now move to essentially you're just manipulating this equation. Let's now move into the next question. And what we're dealing with now is, so far we've been doing a one sample comparison where we've been comparing the sample to the entire population. Now let's do the example where we have two samples and we're comparing them. Okay? And what do we do in this situation? I think just to go quicker, I'm going to switch to the overhead. Is that okay? All right. Do you guys get as much out of the overhead versus the board? Like, which is better for you guys? You guys like the board better? All right, then we'll stick with the board. It might take a little longer, though. Okay. So now we're dealing with the two-sample test for binomial proportions. So this is page 3 of the handout for those following along. And so we're dealing with two samples here, P1 hat, N1, with its own standard deviation of P1, 1 minus P1 over N1. Okay. And so you have two of those samples. You also have P2 hat, N2, and so forth. The first thing you want to do always when you're dealing with binomial proportions is check if NPQ is greater than 5. So that's the first step. Is NP1, Q1 greater than 5? And let's read the question out loud so we know what we're doing. So a study was conducted to look at the effects of oral contraceptives on heart disease in women 40 to 44 years of age. It is found that among oral contraceptive users, 13 women out of 5,000 developed a myocardial infarction. Okay. So our probability P1 is 13 over 5,000. Okay. And the non-oral contraceptive users, our probability of developing a myocardial infarction was 7 over 10,000. So 7 over 10,000. So those are our two probabilities. Okay? And we want to, the question is, are these probabilities the same? So our null hypothesis is the two probabilities are the same. Or are they different? So that's what we're asking. And so you go back and you check if NPQ is greater than 5 for both of them. And you guys can do that, and it is. They're both greater than 5, which is good, because now we can assume that they're both